right. So it's my pleasure to introduce the first speaker of the day, Dmitriy Zanin from the University of New South Wales in Sydney, Australia. And he will talk about the Chern character formula for locally compact spectral triples. Dima,
okay.
you are in the spotlight.
Sure. So I'm really happy to participate in this conference. I so much enjoy listening to the talks, and I hope that my talk will be also interesting to the audience. Now, I apologize that I include too many details sometimes. But since there are, many students, they would probably not understand if I speak without details. So if you think something is obvious, then probably it is obvious. Okay, so initially I was a little bit worried because my talk is not exactly about cyclic theory, but about Hochschild theory. But fortunately, many people already talk about Hochschild theory, so it's probably all right. So let's start. In the big red book, there is a formula which is given without a proof. So here it is, character formula. If you have p-dimensional compact spectral triple, then non-commutative integral of certain differential expression omega of c equal to some expression called Chern character. Okay, so this is true for every Hochschild cycle. I will define later everything. I will define non-commutative integral. I will define Hochschild cycle. I will define what exactly Chern character means in the Hochschild theory, and I will precisely tell you what is omega of c. So, why this formula is important? Because it gives so-called local expression for the Hochschild class of the Chern character. So, just to make it clear, local expression is what is on the left. So, this formula was announced but never proved, at least never proved in published in any publications of Kohn. So a number of authors attempted to prove it with various degrees of success. I presume that many of those authors just listened to what Kohn lectured in various courses and based their proofs on this. But, well, as far as I know, no one succeeded in proving this Hochschild expression for Chern character for locally compact spectral triples. So far, all the theory was for compact spectral triples. And so my aim today is to explain how it works in the locally compact theory. So now I will discuss some very basic things, which of course you are very familiar with. So just to define a framework. So we are working in the B of H, which is denoted here by L infinity. So algebra of all bounded operators on separable infinite dimensional Hilbert space H. So operator is compact if it is approximable by finite rank operators, as always. Now, if our compact operator is self-adjoint, then its spectrum is discrete. It consists of non-zero eigenvalues of finite multiplicity. The only possible accumulation point is 0. 0 may be an eigenvalue, or it may be not an eigenvalue, it does not matter. So if A is compact, then absolute value of A is compact, and eigenvalues of absolute value A would be called singular values of A. And singular value is of importance in all the framework of the non-commutative geometry, because it allows you to define the notion of infinitesimal. So we need the singular value sequence. It consists of all eigenvalues of absolute value A arranged in the decreasing order and taking with multiplicities. So far, this was just a reminder. I understand that everyone knows this, but, well, it's better to remind it anyway. So here come ideals and infinitesimals. First of all, what is ideal? Ideal is a purely algebraic notion, which works in any algebra, but we apply it to our algebra L infinity. So what is ideal? It is linear subspace in L infinity. Since we are working with algebraic setting, our ideal is not assumed to be closed in any norm, including in the uniform norm. So purely algebraic notion of ideal. So what is the condition which defines ideal? If A is in I, and if B is in L infinity, then products AB and BA fall into I. So there is always a trivial ideal of the algebra, just algebra itself. But in L infinity, all non-trivial ideals necessarily consist of compact operators. Okay, which ideals are the most important? Of course, those which are generated by a single element. Such ideals are called principal, and among principal ideals, the ideals which are generated by diagonal operator having numbers k plus 1 power minus 1 over p on the diagonal, they are called LP infinity. So there is more analytic way to define LP infinity, because this is the algebraic definition. But analytic definition is in terms of the singular values. It's given in the next display. So LP infinity consists of all operators whose singular value decrease like k plus 1 power minus 1 over p. And so let me explain why those ideals are important. Exactly because, well, in the non-commutative geometry, they are important because they define infinitesimals of order 1 over p. Okay.
So, sorry, this is not a Schatten-Picq class then?
No, No, it's not Schatten P class. It's weak Schatten P class.
LP infinity.
You see, the notion of weak space, of course, is familiar also in the commutative setting. But in the commutative setting, it appears a little bit ad hoc. While here, in the non-commutative setting, one can simply say that it is principal ideal generated by this sequence. So here it's more natural. Okay. Now, let's define the quasi-Banach ideal. So ideal is quasi-Banach if there is, first of all, quasi-norm. Second, ideal is complete with respect to this quasi-norm. And the multiplication operations from ideal times L infinity are continuous. So just like in the first display. So I norm of AB is controlled by I norm of A times uniform norm of B. Same for I norm of BA. By the way, I say norm while assuming it's quasi-norm, just because it's shorter. Okay, so LP infinity, for example, is quasi-Banach ideal, and it is equipped with natural quasi-norm defined in the second display. Since mu Ka is controlled by the sequence k plus 1 power minus 1 over p, then if we multiply mu Ka by the sequence k plus 1 power 1 over p, you get bounded sequence. So supremum of this bounded sequence is the p infinity quasi-norm. That it is indeed a quasi-norm is rather elementary exercise, but it's not absolutely obvious.
So you don't have to complete here. The idea is already complete.
It is complete.
Already, okay.
It is complete, and the completeness here is actually much easier to check than in the case of the Schatten class. Why? Because convergence in, okay, suppose you have Cauchy sequence, then Cauchy sequence converges in the uniform norm, and convergence in the uniform norm implies convergence of singular values. So then it's rather easy to establish the convergence in this quasi-norm.
Good, thank you.
Okay. Now, I want to emphasize here that it is typically a quasi-norm, not a norm. For p bigger than 1, you can find equivalent norm. But for p less or equal 1, it's not the case. There is no equivalent norm. It's a genuine quasi-norm. Of course, we are mostly interested in the case p equal 1. And on the next slide, we will see a reason why p equal 1 is the most important. So, the notion of trace. Trace is again a purely algebraic notion. We do not assume any continuity property or anything. So, trace is what you expect it to be. It is a functional phi from the ideal to complex numbers, of course, linear functional, which has the property phi of AB is phi of BA when A is in the ideal and when B is arbitrary bounded operator. Equivalent definition that phi is unitarily invariant linear functional. So phi of U inverse AU is phi of A for every A in the ideal and for every unitary U. So, which ideals allow a trace? This is highly non-trivial question, but the ideal LP infinity for P bigger than 1 does not carry any trace. And the reason is as follows, that commutator of the commutator subspace of the ideal LP infinity, that is linear span of all commutators, commutator of A and B, where A is in the LP infinity and B is bounded. This is just LP infinity itself. So whatever trace is necessarily 0. But for P equal 1, this is not the case. We have lots of traces. The most famous one is Dixmuir trace. I slightly modified the original Dixmuir's construction just to make it simpler. So, what's the construction? Take Z plus, take a free ultrafilter on Z plus, then a limit along this free ultrafilter gives you a character of the algebra L infinity. So of the algebra of all bounded sequences. And using this character, you can define a functional trace omega on the positive cone of the ideal L1 infinity, like this, as in the second display. So mu Ka is controlled by roughly 1 over K. So sum K from 0 to N mu Ka is controlled by the logarithm. So when you divide it by logarithm, you get bounded sequence. And to this bounded sequence, you can apply a character which is obtained from the ultrafilter. Now, it is an exercise, though not very simple. It requires certain properties of singular values, that on the positive cone, such a mapping is additive. And obviously, it is positively homogeneous. Now, every mapping on positive cone of an ideal, which is additive and positively homogeneous, allows extension to a linear functional on the whole ideal. Now, you have extension of trace omega to the whole L1 infinity. And since trace omega depends only on the singular values of mu of A, it must be unitarily invariant. Hence, it is a trace. It's called Dixmuir trace. Okay, so let me summarize just few basic things about traces. Here they are. First of all, every Dixmuir trace is a positive functional. So it maps positive operators into positive ones. Every positive trace is continuous. And conversely, every continuous trace is a linear combination of positive traces. Okay, Dixmuir trace is positive, but there are positive traces which are not obtained by Dixmuir's construction. Also, there are traces which fail to be continuous. Next, I told you that there are many traces. How many? 2 power continuum. So you have 2 power continuum ultrafilters, and you have 2 power continuum traces on L1 infinity. Okay, and finally, property number 7, which makes those traces useful in non-commutative geometry. Every trace on L1 infinity vanishes on finite rank operators and moreover on L1. This allows you to kill, under the trace, to kill the terms which are incomputable but small. So that's why it is, well, this property is important in non-commutative geometry, and that's the reason why traces are used there. Okay.
May I have a question?
Yes, please.
So if you are saying that the trace is continuous, you mean continuity with respect to the quasi-Banach norm, yes?
Yes, exactly. This one with p equal 1.
Okay, I see. Thank you.
Okay. Now, here goes the basic objects of the non-commutative geometry. The spectral triple. What it is? Of course, it is a non-commutative version of Riemannian manifold. So, since I am interested in the locally compact spectral triple, I will define it here in the locally compact version. So, what is spectral triple? Of course, it is a triple, as the name suggests. So, first component of the triple is the algebra a star algebra, which is represented on a Hilbert space H. H is the second component of the triple. And what is third one? Third one is a self-adjoint operator D on H, which is analogy of Dirac operator on the Riemannian manifold. So it is self-adjoint, typically unbounded, as you would expect from a differential operator. And there are certain properties which it has to satisfy. So A times D plus I inverse is compact for every A in the algebra. So that's the condition which is necessary for the triple to be called spectral triple. Okay, we need spectral triples with the following properties. So, first of all, if one belongs to the algebra, then obviously resolvent of D is compact operator, and it's natural to call such spectral triples compact. However, if one does not belong to the algebra, then we call our spectral triple locally compact. Next, let's define the notion of dimension. In the compact case, you can say that it is p-dimensional if resolvent belongs to LP infinity. In locally compact case, we have to be careful because the most important point is that the thing belongs to L1 infinity. Hence, we use a pth power. So, spectral triple is p-dimensional if A times the pth power of resolvent belongs to L1 infinity. And the same should work with D of A times pth power of resolvent. Here, D of A is the commutator of A and D, which is supposed to be bounded. Okay, so that's the notion of dimension. And now let's define even and odd spectral triples. If there is a grading operator, then we call our spectral triple even. If grading is not provided, then we call our spectral triple odd. So what is grading? First of all, grading is unitary operator. Then it is self-adjoint operator. Then it commutes with the algebra. And finally, it anti-commutes with D. So that's what grading is. Okay. Now we can define our notions. because so far it was just mostly preparatory material. So there is important notion of Fredholm modules. So what are Fredholm modules? They are non-commutative version of conformal geometry. So here is the definition. Suppose we have F on our Hilbert space H, a unitary self-adjoint operator, such that commutator of F and A is compact for every A in the algebra. Let's define the dimension of Fredholm module. We say that it's p-dimensional if commutator of F and A is in LP infinity. And here goes a theorem. Proof is not very hard, which tells you that there is a relation between p-dimensional spectral triples and p-dimensional Fredholm modules. So, suppose for simplicity that D has trivial kernel, then you can take F to be signum of D. Then triple AHF is p-dimensional Fredholm module if AHD is p-dimensional spectral triple. The non-commutative integral. So what it is? Suppose you have p-dimensional spectral triple. Okay. Suppose you have p-dimensional spectral triple. Fix a trace phi on L1 infinity. Take X, an arbitrary bounded operator. Consider the operator X times 1 plus D squared power minus P over 2. If your spectral triple was compact, this would belong to L1 infinity. If your spectral triple is locally compact, then you should impose the condition that it belongs to L1 infinity. So if it belongs to L1 infinity, you can apply a trace to it. And result of this trace would be called non-commutative integral. Okay, there are many traces. Which one to choose? There is no obvious way. So probably we only should consider those elements for which the notion of non-commutative integral does not depend on the choice of a trace. Such elements are called measurable. So here is the definition. Element is measurable if non-commutative integral does not depend on the choice of a trace. Okay. So now I promised to define.
May I have a question?
Yes, please.
So is it obvious that this definition, or maybe it's not true, does not depend from the choice of the spectral triple? Since somehow you first consider a particular spectral triple, and then having this spectral triple, you define the notion of being measurable.
No, but I mean, what is measurable is the product of X by the other operator. I mean, when he speaks about X, but I mean, in fact, one should speak about the whole package.
And also how.
But if I change my spectral triple, I have different possible D, and in principle, it could happen that for some other D, it will be measurable, but for the first choice, it will be not.
No,
exactly right. This is connected to a particular spectral triple. So if one would like to be careful, it's better to say that the element is measurable with respect to a particular choice of spectral triple, if blah blah.
And is it clear that this set is not empty?
No, it is not clear. That's why the character formula is so important, that it delivers a wide class of elements for which you have measurability.
And sorry, just one more little question. If we would reformulate this definition, demanding that this is always the same, but not for all possible traces, but for a Dijkstra traces, do we get the same equivalent definition or not?
No, it is not equivalent.
There are plenty of discontinuous. Sorry?
Definition is not equivalent. However, the character formula works in full generality. So it works, well, the non-commutative integral of the omega of C, which I will later define, does not depend on the choice of a trace. It is true even for discontinuous traces.
I see. Okay, thank you.
Okay, so Hochschild cycle. So Hochschild cycle is element of Hochschild homology, and it corresponds to the notion of cohomology in the classical geometry. So what it is? It is an element of tensor product, tensor power of A. For this, elements of tensor power are called chains. For a chain, you define the notion of boundary operator. It is defined by exactly the same formula as you would expect it to from the classical geometry. So here it is. Chain is called cycle if its boundary is 0. Since if you take square of the boundary, you always get 0, it follows that every Hochschild boundary is always a Hochschild cycle. Converse is fortunately not true. Next, Hochschild cocycles. What are they? They are elements of the Hochschild cohomology, and they correspond to the notion of, they correspond to the homology in classical geometry. So what are they? They are linear functionals on the tensor product, on the tensor power. So for them, you have a notion of cobound. It is defined by exactly the same formula as you would expect it to be. So it is here in the display. Cochain is called cocycle if its coboundary is 0. Again, if you apply coboundary twice, you get always 0. So Hochschild coboundary is always a Hochschild cocycle. And by the way, you can easily check that there is an analogy of the Stokes formula from the classical geometry. It is verified element. Okay. Next, Chern character, the primary object for which we want to have a local formula. So, first of all, if we have a p+1 chain, then we can define expression like in the first display. So for elementary tensor, A0 tensor A1, etc., tensor AP, we can consider product K from 0 to P, commutator F and AK. And this product belongs to L1. And when something belongs to L1, you can take a classical trace of it, can you? So we can define cochain by the formula in the second display. So CH of elementary tensor product is 1/2 trace gamma F product K from 0 to P, commutator F and AK. So it is an exercise that this cochain is actually a cocycle. And this cocycle is called Chern character. So I have to emphasize here that this is a Chern character in the Hochschild theory. Of course, Chern character in the cyclic theory is a different thing. But in the Hochschild theory, that's what it is. And it is considered hard. It is considered non-trivial to compute this. And so we want local expression of this. And now let's introduce this local expression. But for this purpose, we need certain conditions on our spectral triple. So what are those conditions? First of all, we require that triple is infinitely smooth. So this is a rather technical condition. Basically, it is the analogy of the classical Riemannian manifold to be infinitely smooth. Next, we want our spectral triple to be p-dimensional. So I just remind this condition here. And finally, we need condition 3, that L1 norm of A times lambda resolvent of D power P plus 1 is big O of lambda inverse. So what this condition means? It is roughly some estimate on the heat semigroup of the operator D, roughly. It is the condition which automatically follows from condition 2 in the compact case, but in the locally compact case, it does not, and so we have to impose it. Having those hypotheses, we can state the character formula. So here goes omega, the promised local expression for the Chern character. So omega is defined on elementary tensors by the first display. So omega on the elementary tensor is gamma A0 product K from 0 to P, commutator D and AK. So, and here goes the theorem. Suppose you have a spectral triple which satisfies the hypothesis.
Wait, Dima, but K goes from 1 to P, right?
Yes, sorry, K goes from 1 to P. I'm sorry, that's a typo. Thank you. Yes. So if C is a Hochschild cycle with minor additional property that is localized, so in the classical geometry, think that components of your Hochschild cycle are compactly supported functions. So that's what localized means. I will precisely define it a little bit later. So we have that phi of omega c times 1 plus d squared power minus p over 2 equal to the Chern character for every trace on L1 infinity. So continuity is not assumed. It works literally for every trace. Okay. So,
sorry, this is strict equality or only equality in Hochschild cohomology?
So it is genuine equality. So if you take Hochschild cycle C, then left-hand side would be equal to the right-hand side.
Okay.
But don't you the phi of 1 over n is equal to 1?
Yes, you are right. I omitted the condition that trace is normalized, that is on the sequence 1, 1 over 2, 1 over 3, etc. It takes value 1. This is, of course, important condition because otherwise we can multiply the trace by a scalar.
Yeah, these are numbers.
Yes. Okay. So now let me tell you about the basic steps in the proof. Of course, I'm not proving anything, but steps are here. Oops. So first of all, hit semigroup asymptotic. If C is a Hochschild cycle, then you can take omega of C multiplied by 1 plus d squared power 1 minus p over 2, multiply by exponent of minus s squared d squared. You get trace class operator. Take its trace. It is exactly p over 2 Chern character times s power minus 2 plus small thing, big O of S inverse, when S goes to 0. So proof is long, combinatorial. It basically goes like this. The difference between left-hand side and right-hand side is a sum of tons of coboundaries. And coboundaries vanish on every Hochschild cycle. So that's the idea of the proof. Okay, next. Since there is a formula which relates complex power of the operator with respective heat semigroup, from this theorem on the previous slide, we can get analytic continuation of the zeta function. So here is the zeta function in the first display, and it is holomorphic. Well, a priori, it is defined on this half plane, real part z bigger than p. But it allows analytic continuation to a bigger half plane, real part z bigger than p minus 1. Of course, there is an exception, a point z equal p. This point is a simple pole. And since it is a pole, there is residue. And what is the residue? Residue is p times Chern character. But how to deduce the character formula from this? It's highly non-trivial business. Let me explain you the theorem. So theorem well, which is the core component of the proof, is as follows. If A is the element of your algebra, then the function like this, like in the display, 1 plus d square power minus z over 2 a power 2z minus z power of compact operator inside is L1 valued analytic in the bigger half plane, real part z bigger than p minus 1. So here L1 is of course just trace class. That's really hard result, and it is based on the following integral representation. I only show it on the next slide. It's quite complicated. Here it is, that if you take positive operators capital A and capital B and y like this, a power 1/2, b a power 1/2, then the difference b power z b power z a power z minus y power z is equal to something in the right hand side, which is supposed to be better. Supposed to be better. But that it is actually better is like 20 pages of computation. Okay, and how does it help us? Here is one more intermediate result. If we have an operator V, which is in L1 infinity, and if we have bounded operator, then if the zeta function, like in the first display, is analytic in the bigger half plane, except at 0 where it has a simple pole, then AV is measurable. That is, trace of AV is a residue of this zeta function. Now, let's combine all these 4 results and get a proof. So, suppose C is localized. So what does it mean? Localized means that there is some A in the algebra such that we have equation like in the very first line. So once again, this corresponds to the classical notion of compactly supported function. So the components of your cycle are compactly supported functions if you are in the classical geometry. Then you have a power 2z times omega c is omega c. Then you can write your zeta function like this. Trace of omega c times 1 plus d square power minus z over 2 times a power 2z. And this is analytic by the theorem that zeta function is analytic. Okay, now the non-compact, non-compact expression 1 plus d square power minus z over 2 is replaced with a compact expression because the difference between this zeta function and this zeta function is analytic, L1 valued analytic. So its trace is analytic function on the bigger half plane, real part z bigger than p minus 1. Now, if we denote this operator by v, then we get that this zeta function is analytic on half plane, real part z bigger than minus 1 over p with simple pole at 0. Now we can compute the residue and complete the proof. So a combination of those four intermediate theorems gives us the character formula in the locally compact case. Okay, I think I am exactly on time, so.
Yes, thank you, Dima, for your crystal clear talk. Are there questions? We have time for questions.